So once again, in general, for any rational function f of x, if the limit as f of x, the limit as x approaches infinity of f of x minus mx plus b equals 0, or the limit as it approaches negative infinity for f of x minus mx plus b equals 0, then the line y is equal to mx plus b is the slant asymptote, because the vertical distance between the curve and the line is going to approach 0. So if we consider the function f of x is equal to x squared plus 1 over x plus 1, you can see that this is a rational function. Where the degree in the numerator is one more than the denominator. So I'm going to take it, I'm going to divide it out. If f of x is equal to x squared plus 1 divided by x plus 1, then I'm going to factor out that x plus 1 and I'm going to get a coefficient of 1 for x squared, of 0 for x, and of 1 for the constant. We're going to carry down the first term, and that's going to give me 1. Multiplied by negative 1 is negative 1. When I add 0 and negative 1, I get negative 1. When I multiply that by negative 1, I get positive 1. And when I combine those, I get a remainder of 2. So my function, x squared plus 1 over x plus 1, I can rewrite as x minus 1 combined with 2 over x plus 1. The limit as x approaches infinity for x plus 1, sorry, it was x minus 1, looking here, x minus 1 plus 2 over x plus 1 minus x minus 1 is going to equal the limit as x approaches infinity for 2 over x plus 1, which is going to approach 0, which means y is equal to x minus 1 is the equation for the slant asymptote. What happens when the degree of the numerator is greater than the degree of the denominator by more than a difference of 1? So if I took f of x is equal to x cubed minus 1 divided by x. Well, if I'm dividing this out, then I'm going to divide x out of x cubed plus 0x squared plus 0x minus 1 in order to cancel out the x cubed. I would have to multiply this by an x squared. When I subtract them, they cancel out. That becomes 0. There is nothing I can multiply to make it match up with the 0x. And then I'm left with this remainder of -1, which means that when I divide that out, f of x is going to become x squared minus 1 over x. Well, using that limit as approach 0, this is the piece that is going to approach 0 as I shoot off to infinity. So if I take the limit as x approaches infinity and I want to make it equal 0 for x squared minus 1 over x, then I would have to take away an x squared in this case. And the limit as x approaches infinity for -1 over x does approach 0, which means that in this case, the nonlinear asymptote would have the equation y is equal to x squared. This is a very bizarre one because I'm going to have that asymptote at y is equal to x squared, where my function is going to approach that line on the left-hand side and on the right-hand side. Okay, so to summarize, if the degree of the numerator is higher, then the graph has a horizontal asymptote at y is equal to 0. If the degree of the numerator is higher, the graph has a slant asymptote obtained from dividing. If the degree of the numerator equals the denominator, then it's going to have a horizontal asymptote obtained from dividing the leading coefficients. And a graph will not have a horizontal asymptote and a slant asymptote. It's going to be one or the other. Vertical asymptotes can occur when the function has a non-canceling factor in the denominator. So, what happens when the degree of the denominator is greater than 1? Will synthetic division still work? Well, in this case, we're going to use long division. We're going to divide it out, and we're going to say that if we're dividing out x squared plus 4 from that numerator, x cubed plus 4x squared plus 5x plus 16. Then, in order to make that x squared match with the x cubed, I'm going to multiply this by x once, which is going to give me x squared times x gives me x cubed, and the 4 times x is going to give me 4 x. Remember that I can only combine like terms. So when I am subtracting those from each other, then the first term is going to cancel out to 0. Good. The second term is not going to change at all. So that's going to carry straight down to be 4x squared. When I take the 5x and take away 4x, then I'm left with a singular x. And when I carry the 16 down, it's still going to give me plus 16. Now I need to make the next set match. So I'm going to see what can make the x squared match with the 4x squareds. Well, in this case, obviously, I'm just going to multiply it by 4. And so when I multiply it by 4, x squared times 4 gives me 4x squared. And 4 times 4 gives me 16. And when I subtract those out, first term gives me 0. Last term gives me 0. But the x will carry through and still just be a remainder of x. So when I'm taking the limit as x approaches infinity for x plus 4 plus a remainder x over x squared plus 4, and I take away what I factored out, x plus 4, then that's going to leave me with the limit as x approaches infinity for x over x squared plus 4. I'm going to multiply the top and the bottom by 1 over x squared. Which is going to give me the limit as x approaches infinity for 1 over x divided by 1 plus 4 over x squared. I know as it approaches infinity, those are going to approach 0, which means that I'm left with 0 over 1, which does approach 0, and that follows the rules that we had, and we can say y is equal to x plus 4 is a slant asymptote. All right, you give this example a shot. Same process.